sessions. Okay, so we'll start with the this section. Let's go to our notes. Okay, if you have a surface, say surface, and then a path on that surface. Okay, so suppose you are here. This is a path. So this is a path. So parameterized surface. Sorry, parameterized path on surface S, right? So this is surface S. Okay, and you know that the R of t, R prime of t, that's the give you the tangent factor. T of path R. Okay, so it looks like something that looks like this one here. Okay, so this is R prime of t. Okay, and so suppose you have a, let me check, forget something. Okay, all right. So this is the parameterized, sorry. Okay, and the surface is given, sorry, surface S is given as implicitly. So this is implicit expressions. Okay. All right, so let's see that one here. So if you do these computations, so if you have, so now x of t, y of t, z of t. So this is f along the path or curve r. Okay. Okay. And you take d dt of each of this left and right hand side. Well, the right hand side is easy. Okay. And the left hand side, well, you know, this is a composition, so chain rule applies. So with chain rules, what you have is that, well, you got to compute this one here. So df over dt, right? Sorry, f is a function of x, y, z. So for x first, and then dx dt. Okay? Because of chain rule, then you have the second path, dy over dt. Okay, and then you have the third one. Third one is df over dz, dz over dt. Well, which you can write this down as gradient of f. Okay, dot, what's that? that's a factor of dx dt, dy dt, and the okay. Okay, and so this, well, what is that called? What is this factor here? This is nothing but what we call dr over dt. Okay, so the tangent line, tangent factor, sorry. Okay, so this tangent factor, so this r prime. All right, so what does it mean? So you have two factors, gradient times tangent is 0. What does it tell you? Dot u dot v equals 0. What does it? What this factor tells you about? Hello. Am I still on?
Yes, sir.
All right. Okay. What does it tell you? If you have two factors, you dot the dot product 0.
They're perpendicular, sir.
Perpendicular. So this perpendicular to uh, this is a tangent. Okay. And you know something that perpendicular to tangent, let's recall this is normal factor. Okay. Normal of what? This is normal factor of the of the say of the uh, uh, tangent plane. Okay, so we have two tangent. Here we have tangent factor. You have also tangent plane. Okay, so if we return to the picture, what we have is that, well, because the green one, the r prime, so this is the normal, right? So this normal. Okay. So where is the tangent plane? Where the tangent plane should be something that looks like this one here. Huh? So this is tangent plane. Okay. All right. And uh, here. Okay. So the gradient is nothing but the normal factor of the tangent plane. So we know the equation for the tangent plane. How do we know then the from this fact? Okay. So what is the equation for tangent plane? So the component uh, is gradient of f. Okay. What is gradient of f? It's nothing but the df dx, df dy, df dz. So this is the as a plane. This is the coefficient for the for tangent plane. What does it mean? So the equation for tangent plane would be somehow the x at um, what do you call okay, the f dy and y minus y naught, the f dz equals 0. Okay, so recall that the equation for the plane is ax plus by plus cz, right? And where ABC is the normal to that plane. Okay, so equation for a plane containing the point um, uh, with normal ABC is A, B, Y naught plus C. Okay, we call this one. So this is our tangent plane. Okay, questions? All right, so let's continue with the example. Now the example is easy. So the question is find equations for tangent plane of the paraboloid para z x squared plus y squared at the point, so let's see, say 1, 1, 2. Okay, so that's a point on the paraboloid. Okay, all right, so let's see. This would be our x0, y0, z0. Okay, so first we need to find the uh, the the normal for tangent plane at there we go. So what is this? First, what is f? Well, from this one, the equation for a surface would be, well, let's put it implicitly. So this would be x squared plus y squared minus z. Okay. So why don't you choose z minus x squared minus y squared? That's up to you. It doesn't matter. It gives you the same answer. Okay. So what we have now. So what we have moment is that here, easy. The factor would be derivative to x is 2x, derivative to y, 2y, and minus 1. Computed at 1, 1, 2. So that equals 2 to negative 2. Okay. So then that is the normal factor. So equation for the tangent line, so tangent plane. So this is 2x minus 1 plus 2y minus 1 also. So this is minus 2, z minus 1. Okay. And if you prefer, you can write this down. Z equals, what is that? You can cancel the 2. Right? Okay, so this is just 1. You put here z1 plus, doesn't matter. So z equals, let's say 1, not 2 anymore. That gives you x plus y, 1 minus 1, that's 0, minus 1. There we go. Okay. Then that's the equation for tangent plane. Questions? All right, that's the easy part. Okay, so then let's do the approximations by tangent plane. So 1D analogy. Okay. So in one variable, you have, this is a graph of y equal f of x. Okay, so this is a, say, point x naught, and this is that's a tangent line. Equation for tangent line is, oh, right, f prime of no, times, that's the equations. Okay, that's the equation. This is an approximations of the value of f near x naught. Okay, so here, for example, x. So instead this value here, we compute this value. Okay, so this is that's the real value of f of x. This is the approximations to right, we got stuck. And you recall this one here, differential. Okay, what's differential? What is dy? Okay, so in this case, dy is dx. This is differential x, this is differential y. Okay, so dy this that's going to approximate delta y. This is the real error. This is the actual error. This is the estimate error. Uh, this is approximate error. Okay. So then the approximate so f of x, right, is approximated by there, okay, plus dy here. Okay, so what is dy? Dy is nothing but okay. So how to measure that one? Okay, so the same thing as the in two variables. Okay, in two variables. Okay. So when you have a say a plane and you have a tangent plane, sorry, a surface. Okay, so this is say so C equals okay, right. For example, if you have a point here and this is the value, okay, so differential of f, okay, of f is the f. What is the f? That's so we check what's derivative of this here is f prime. So in this case, what is prime? All right, so prime is replaced with the this, okay, dot with dx dy. Okay, so what is that? Okay, so dx computed at 0 y 0 times dx plus df dy times dy here. Okay, so this is differential of f, differential of x, differential of y. Okay. And this going to approximate that one. Okay. So this is a good approximation for using tangent plane actually. Okay. So this is the real value. And over here, this is the approximated value. Okay. All right, so let's go with the one example of the right. So this is tangent plane. See, differential approximation. This is differential. Okay, let's pick up a problem. Okay, so let's go to exercise. Say problem 9. Okay, let's see problem 9. Let's pick up. Oh, sorry. I should say so. This is a problem. Okay, so we compute total differential. Oh, sorry. I should mention that this is the also called total differential of f. Okay, so because it's total, it's just a sum. Okay, that's the idea. All right. Let's see. We use dz, so dz is the f. Okay, because z equals f of xy. Doesn't matter. Okay. To approximate the change in z as xy moves from p to q. Okay. So let's see. From p to q, the x moves slightly, right? And the y also moves slightly from 1 to 1.02, from 1 to 0.99. Okay, so the when p moves to q, say, I should say it like this. So let's see, this difference is delta x. This difference is delta y. So this is dy, this is dx. Okay, you see? So the first one becomes 0.99. So that's delta x. That is negative 0.01, right? And dy from 1 becomes 0. From 1 become 1.02. There you go. That means the dz is, well, let's compute this. Okay, so let's compute this one. That's easy. Gradient of z. So derivative with respect to x. So that's 4x y. And then derivative with respect to y. So that's going to be 6 square y squared. Okay. Well, this is computed at 1 times this 0.01 0.02. Okay. So 1, 1. You plugged in 1, so this is 4. This is 6. Okay. 4, so negative. This is 6. So 0.1. Oh, sorry. I should say this one. So negative 4 plus 12. So that's going to be 0.08. Okay. So what this means is that when P moves to Q, the Z changed by 0.8 approximately, 0.08 approximately. Okay. Okay, so that's how we compute that one. Let's pick one problem again on some wood problems. Where is that thing? Okay, so let's do the 29. Oh, forget this one before we finish one. Can someone compute this one though? Z when 0.99, 1.02. What does it mean? So compute 2x squared y cubed. When x equals, if you have a calculator, please compute that one. What's the value of this? Compare with this one. What you get? 2 times. Mm, 0.12. What you get here? Say 4 decimals. Use 4 decimals to get this one. What you get?
I got 2.0802, sir.
2 point, again, 2.02.
0802.
All right. So that means delta Z is, sorry, 0802 minus, well, the value when at 1, 1 is 2. So 0.0802. Okay. So here, this is the Z. So this approximate sorry, not the delta Z. Okay. So that's what our computation means. All right, questions? Not, then let's go to the, let's see. Well, that's the same thing. 29, only part A. We'll do the part B also. Okay. Let's see. Or do the second order approximation first. Okay. So the second order. Okay. So recall Taylor or Maclaurin for one variable functions. Okay. So the function f of a is approximated by um, order 2. On the order 2. Okay, so on the around x0. Okay. Plus f prime of x naught. Okay. Then x minus x naught. Okay, so this is the first order. Okay. And second order is that x has x0 squared. Okay, now so this is our second order Taylor approximations. Okay. Now the for two variables we have a similar thing. Well, this is uh, just kind of the magic. I just give you the formula without deriving those. For two variables, you would have something like this. That's f of x0, y0 times, well, we know this, the f prime um, is replaced by gradient computed at 0, x0, y0, times this. Okay. And what about the second derivative? Well, the second derivative, we have now second partial derivative, but partial derivatives, we have a three kinds. All right, so this is first order. The second order is, well, what happened to the, we have this one here. So fxx, right, this is derivative. And then you have also f xy. And you have also f fyx. And finally, you have this y. Okay, so that's second derivative. So for second derivative, we still have this. Okay, and okay, this should, okay, plus it's also multiplied by plus this. Okay, so the second order term is this one actually. Is, sorry, let's see. 1/2. Let me just rewrite this more neatly. It's x square, sorry, look at the square. And because these are actually the same, right? So we have two of them. And you have okay, there. Okay, this is second order. Uh, so now this is the, with the second order, this is the, what we call the second order Taylor approximations. F around, so near x0, y0. Okay, so we'll do one example for this one. Uh, where is that thing? Here. Okay, no, that's correct. Okay, so we'll do 29C, 29 here. Okay. So, okay. All right. So given the function is like this one here. So 1/2, not 1/2, square root of x squared plus y squared. Uh, find the second Taylor approximations around 3, 4. So that's x naught, y naught. Okay. Estimate this one, f 3.1, 3.9. Okay. So in this example here, let's go back to this one. So 3, 4 going to 3.1, 3.9. So in this case, the x mean x naught, so this x naught. So delta x is, what's delta x? So this is nothing but x mean 3, so 0.1, right? Delta y is, okay, so this one is negative 0.1. Okay, so let's look at the first order approximations. Okay, so f of x, y is x plus y squared power 1/2, that's square root. Okay, so A, first order approximations. Okay, so using first order approximations, we have x of xy is approximated by There you go. Plus the f at there. Okay, then what is this one? Oh, it's nothing but the gradient. So x naught, y naught, dot, so delta x, delta y. Okay, so then let's compute this one. That equals, so plug in 1, 1, right? Sorry, 3, 4. So that's 5, right? Plus, let's see, what is this one here? So gradient, so partial respect to x. So this one. So the power reduced by 1, negative 1/2 derivative to x. Okay, so you have 2x over, okay, that's the same. Dot what you have there. Okay, so it's 5 plus what do we have here? 3, 4. So it is 6 over 5. Is that correct? 5. This is 2. Oh yeah, 6. And this gives you 8 over 5. Dot. Okay. So what you get there is 6, 5 minus, we can minus. Oh, that's wrong. Yeah. So what you get there is 0 0.1, 0 0.2404. Okay. So 4 there. Okay, so that's first order approximations. Okay, and B now. Second order approximations. Okay, let's this is first order. Let's now just find the second order. So we need to find this here. Okay. So what we get is second order first order plus what we called from here second order Taylor. Okay. Second order term of Taylor plus from Taylor. All right, so let's just compute this one here. Okay, let's compute. We know fx is 2x over, okay, fy is 2y over, okay, and then second derivative, this one. Okay, so derivative of the top, 2, 2 times this. Sorry. Okay. That's this one minus 2x times derivative of this, which is another 2x. I'm wrong. I am wrong. All right, derivative of 2x, this 2 times this one. Okay, subtract 2x times derivative of this. All right, so it becomes this times 2x. Okay, over derivative square of this. Right. Okay, so if you simplify this one, what you get there? Actually, we don't need to compute it. Just compute at 3, 4. Okay, so just plug in 3, 4. That's easier. Okay, so if you plug in 3, 4, you get to 5. That's 10 minus this is 2x, 6, 36 over 5. So 4x squared. Yeah, over this one here is 25. Okay, simplify this bit. This is what you call 7.2, right? So 2.8 over 25, whatever the number there, FYY, that's the same. Just replace the so it's the same thing, minus, so which is 4y squared over x squared plus y squared. Compute 3, 4. That equals to what you get there. All right. So that's 10 minus this is 4y squared instead. 4y squared. This is 4. 16, 64. Okay. So that means 10 minus that is okay. So negative 2.8. Okay. And then you compute fxy. What is fxy? X derivative is respect to y. Okay, and that's easy because now it becomes power 1/2, power 1, 3 halves. Okay, so this becomes 2x power negative 1/2, 3 half times derivative of this with respect to y. So, okay, so for xy, okay, compute at 3, 4. You get something that looks like 4 times 3 times 4. 12, 12, 16. This is 5 cube there. Okay, and the second order term is is 1/2 times fxx times delta x xy, this is square, delta x delta y plus this is 2 delta y squared. There, computed, plugged in 3 4. Okay, well, we know that one. We computed already. 28 25 times this one square, the x square 0.10. 2 times of this, 2 times of this one, so 120 per delta x times delta y. What's delta x times delta y? Okay, so negative. Okay, plus again, this is the same, but instead of this, we have negative. Fyy is negative. Delta y there. And that's cancel. What remains is this one. So 60 over 25 negative 3 0 1. Sorry, I was wrong. Too many zero. All right. So this is it. So the second order approximations f of what is that? Sorry, forgot that one. 3.1, 3.9 is approximated by, all right, first order approximations. What is first order approximations? 4.96 minus there. Well, you can compute this number, calculator, and make comparison also. You use calculator. Okay, questions? If not, then let's take a break. Take 5 minutes break.